Okay, this is the second part of the introduction, and now we will go into some more detail in the method that I will follow to explain theorems. And what I want you to keep in your mind is that the notion of a theorem comes from the word theoria, and theoria is what allows you to see behind some obstacle. So it's this idea of a partition spectrum again, which becomes very, very important. And of course, the abstraction and the invariance that follows from it. So let me introduce the method that I will use. It's this model that I call the model of natural communication. And as I said, my approach is not target-oriented, but it is obstacle-oriented. So philosophically, I do not start from any particular type of ontology, even for mathematical problems. So I do not classify problems as geometric, algebraic, or combinatorial, or probabilistic. I think that they are different manifestations of some deeper obstacle. And it is this notion of an obstacle which prevents you from seeing directly through the truth which is behind a theorem. So the model of natural communication, first of all, it is called communication because it allows different levels to talk to each other. So for example, here, you can imagine that you have the level, the top level, where the obstacle is located. What prevents you from going from this side to the other side, pictorially. And I can give a very, very simple example. You imagine that this line is the real line. The real line consists of all real numbers. And you just exclude a single element from the real line. Let's say that the exclusion happens here. Immediately, the simple connectivity of the line is broken at this point, and you cannot follow a linear path to go from here to here. And the idea is that in this very, very simple case, you are obliged to start circulating around this obstacle which has been caused from the exclusion of a single point from the real line. So my top level will be the level where the obstacle is located, and this level below, it is the level which will allow me to build in some type of communication between the level where the obstacle is and this lower level is. Of course, in order to be able to do this, I need some kind of criterion of equivalence which will pertain to this lower level. And this is what eventually will form my partition spectrum. Now, in order to be able to move from the top level to the lower level, I need some kind of bridges. I cannot move without having some kind of bridge which will give me a connectivity path to start navigating and circulating around my obstacle. So as you see, in case you locate some obstacle, what you start doing is that you start going away from the level where the obstacle is. So instead of moving towards the obstacle and hit yourself in the imaginary wall of the obstacle, or go and fell inside the hole, okay, if we think of an obstacle as a kind of a topological obstruction, what you do is you move away from the level where your obstacle is. And this moving away needs some kind of code. So the bridge that I will build needs somehow to encode some essential details of this level, excluding the obstacle. That's why I call this bridge the encoding bridge. As soon as I manage to build up this bridge, I have to find a criterion of equivalence which will allow me to build what I call a partition spectrum. Partition spectrum is a kind of a screen, an epiphania, where I make things to appear in blocks, in pixels, in equivalence classes. Now this is formally called an equivalence relation, but I will not strictly follow the set theoretic definition of an equivalence relation. But usually I will think that an equivalence relation comes through some algebraic means, and in particular through the action of some group. The notion of a group is related with the idea of a symmetry. And symmetry means that I have some criteria to make things that I measure to have some similarity and some congruence. So it is this idea of a congruence relation which is manifested in terms of symmetry. So I will think that this level here is built under the action of some group of symmetry which is unifying things under some pertinent congruence relation. Having moved to the level of a spectrum, so having managed to give rise to a screen, then I'm able to distinguish different blocks or cells in this partition, and all of these blocks, they are mutually exclusive and jointly exhaustive, so they exhaust completely the spectrum. Having managed to build the partition spectrum under this equivalence relation, or to give this qualification in terms of the action of some algebraic group, then I haven't finished yet, because I'm still here in this point down here. So I have to be able to invert this encoding bridge. Okay? The code that I'm talking about in this case can be based on a geometric or a topological or even a harmonical criterion, but it can be modeled algebraically through the action of some group. Or more generally, the action of some category. But let's think in terms of of groups, because what you can do in groups is that you are able to invert. For this, a necessary condition is the existence of this notion which is called a neutral element under some operation. For example, if you have the operation of addition, the neutral element is the 0. If you have multiplication, the neutral element is the unity, 1. But these are very simple examples, but we can abstract them properly. And the essence is that if you have, in this case I'm talking about, you have a group structure, you are able to invert. So you are able to take this encoding bridge and to start decoding by the inverse of this bridge the partition spectrum that you have managed to build. Now, what it means to invert is that you are able to go back to the initial level where the obstacle is located, because the obstacle is not located in the partition spectrum. The partition spectrum doesn't have any obstacles, and that's the purpose that we have built it. The purpose is to get back to the initial level of the obstacle, and this happens through this decoding bridge. As soon as I manage to complete this kind of round trip between different levels, I have established a communication domain between these two different levels. And this consists, in my conception, in a kind of generalization of the notion of a geometric area. So it is an abstract area which I can use in order to navigate and in order to discover what is hidden behind the obstacle. This is a very important idea, is that all the invariants that you can get in the partition spectrum is due to the obstacle. So the idea is that the obstacle is the real source of any invariance that you will have. And you will see many examples in the theorems that I will talk about, that all the invariants which gives the truth of the theorem is due to the location and circulation around the obstacle. So the obstacle is the source of invariance. And this invariance we try to figure out in order to embrace the obstacle, and in order, in the case of a theorem, to find the truth of the theorem. Not the proof itself, which can be arranged deductively, but the conception of this circulation around the obstacle that makes this theorem important or not important, according to some criterion. Now, this round trip between these two different levels, the level of the obstacle and the level of the partition, it's called metaphora. Okay, and metaphora, I use this word because the word metaphor, it is very loaded linguistically, and that it has meanings which are not relevant at all to my context. So I use the original word for it, metaphora, to mean exactly what I have explained up to now. Now, let's see very briefly what are the properties of this model of natural communication. So the communication is between a level where an obstacle is located and the partition spectrum, always, but possibly it is not immediately possible to make a kind of a partition spectrum which will consist of blocks which will contain all the information, all the invariants of the upper domain where the obstacle is. So in this case, and this is very relevant to what I was talking before about abstraction and this process of percolation, I need to do it gradually in different steps. So I need to start encoding, not in terms of a single bridge that you see here, but gradually by a composition of encoding bridges. So the partition spectrum is not formed completely at this level here, but is formed at a deeper level here, which requires the composition of different encoding bridges. Now you see that the deeper I go, this can be iterated, then my partition spectrum, as soon as becomes complete and I'm able to extract information from the partition spectrum, I'm obliged to follow the same series of decoding bridges in order to arrive back at the level of the initial problem. As soon as I manage to perform this series of compositions, then I return back to the initial level, and in this way the obstacle is not only evaded, but I manage to discover the invariance which is hidden behind it. And this is what will give what I call the truth of a theorem. That's the first property. So it is the extension in depth of natural communication. The second property is what I would call the property of juxtaposition. You see that these natural communication blocks can be composed not only vertically, so by going deeper down by a series of encoding bridges, and inversely by the series of decoding bridges, but I can compose a decoding bridge with an encoding bridge of a different level. Of course, they have to annihilate each other so that I can open up a new block which will be juxtaposed and adjoined to the initial one. So this is the idea of extension in the horizontal direction. And the third, it's quite obvious, is that if I'm able to perform the communication between these two levels, I'm able to invert the whole thing, so I can see it upside down, and it's totally symmetric under this inversion of the whole metaphora. The idea here is that a metaphora has always some kind of orientation, and an orientation is a property which has a binary character and can be inverted in a unique way, since it is binary. So these are the three properties which characterize algebraically the model of natural communication, which I will use as a method to talk about theorems. Now you may question why I call it natural. And I have to explain why I call it natural. The idea is that the encoding and the decoding bridges I'm able to build, they should not be arbitrary. They should be based on some criterion of naturality. So it should not depend on any type of ad hoc or subjective choices. They should have some kind of universality. So my code needs to have some kind of universality and objectivity. And in particular, it needs to have some type of symmetry. And the idea of symmetry is not subjective. It is an objective criterion when I use a group, for example, to express some notion of symmetry. So a symmetry, as an algebraic property, is abstracted from the particularities of the situation that I examine or it can manifest. Okay, this is, for the time being, the notion of naturality, although it has a deeper meaning, which is based on category theory, but I will not go towards this at this point. I would like now to explain very briefly what is the relation with architectonics and why I consider that the model of natural communication is especially adapted to think about theorems in relation to architectonic relations. Okay? So let me start again from the top level where there is the obstacle. Of course, in order to put yourself in a position to start thinking about obstacles, or to start doing mathematics, or to start doing architecture, or any other subject, you need to be able to start wondering. So this is a necessary condition to start thinking. It is the wonder. Now, starting to wonder, you need to find a reason that somehow is related with the obstacle that you locate because of some directly inaccessible thing or some deeper truth. So this is the level of, I call it logos, okay, because that's the original name of this setting. It means the why question, basically. And then logos refers to the speech and to the communication, so it's particularly relevant and important from my perspective. And then you need an archi. An archi is a kind of a beginning, a starting point. And the word architecture and architectonics starts from an archi always, which is a beginning. So the idea is that as soon as you are able to locate some obstacle, you need an archi to make you start moving. But in order to be able to start moving, you need to be able to bridge the level where the obstacle is with a different level which will contain some kind of spectrum, okay, this partition spectrum that I was talking before. So in my reading, the encoding and the decoding bridges pertain to the architectonics of the thinking. So both the encoding and the decoding bridges They are first of all a kind of scaffolding which gives you the possibility to move between different levels and to make them communicate to each other. Now, as soon as you have made an architectonic bridge, it should be, by construction, should be natural. Otherwise, it will not be stable and it will fall with the first wind. This is what I meant before by this idea of naturality. So you need to be able to build something which is stable. So it is natural and it is based on some property, for example, of symmetry. Or it needs to express some kind of congruence. Then you are able to build this partition spectrum here, about which I talked before. And this now, in philosophical terms, is the level of the doxa, is the doxastic level. Okay? Because it's up to you if you will see the phenomena as epiphenomena, or you will use the phenomena in order to use the decoding bridge back to go to the initial level where initially you started from and the obstacle is located, and then you are able to find an invariance. So if you stay only on the spectrum without any qualification, then in many cases you will face what is called an epiphenomenon. So it is necessary and sufficient to come back to the initial level, and in this way what you complete is what I would call in philosophical terms a praxis. So it is a praxis which is enclosing a domain of communication. It makes possible to transcribe from the initial level to a spectral level, and eventually to be able to make this circulation around, which I have called metaphora. Here is what the spectrum looks like. So you can see that you have a series of different blocks which are arranged along a navigation path. They are parallel to each other, so they do not intersect each other, but somehow they fit together on the basis of some criterion. In this case, you have a criterion which is based on color. So this is the idea of chroma, how you make a scale which will have the characteristic of chromatics. So chromatics basically the ability to distinguish different blocks in terms of colors. And the mathematical idea of a color is that a color is what characterizes an area. An area by itself cannot be abstracted from the geometric domain if it doesn't bear some color, if it doesn't have some temperature. This is another type of partition spectrum, and I present you this because it is related very much with this notion of abstraction as percolation that I talked before. And this is how I think of a kind of a filter which is able to give a partition spectrum with respect to a domain where an obstacle is located. So first of all, you see the different colors, you see the different blocks, but you see that they are arranged in a way like an onion ring, and they give rise to what is called in mathematics a vibration. So this is a very characteristic type of vibration of the sphere. Here, why we have a partition? Because if we start from the initial level where there is no distinguishability at all, you have just a shadow, then on the basis of some symmetry criterion, you start to make distinctions along this dark shadow, and the distinctions are always in terms of area, and the area can be abstracted if it bears some color or temperature. So this is a kind of example to see what type of partition spectra we are able to build. And these partition spectra are not necessarily only of a visual type, but, for example, in the quantum world, we need to be able to make spectra which resonate and synchronize, so they are sensitive in what I would call the harmonics. And this idea of harmonics comes basically from, you can think of it in terms of music, the initial origin, the Pythagorean harmonics, but now we think of harmonics in terms of quanta, okay, in quantum mechanics. So we have a very, very elaborate theory of quantum mechanics and quantum field theory. And we talk about harmonics, although we do not call them like this, but we call the harmonics as quanta. Okay? And the quanta, they are not geometric. So it is able, you are able, and this is where a lot of things of our modern technology is based on, you are able to resonate and synchronize from the macroscopic level to the microscopic, where electrons, for example, are. So the partition spectrum now is more elaborate, and it can be sensitive to quantization. So it can somehow not see quanta, because not only photons, for example, but you can deal with matter and you can deal with electrons on a quantum level. For example, you can have superconductivity, you can have this type of things which are called now topological insulators, and this kind of things which are based on a behavior not at the microscopic level, not at the macroscopic level, but at the microscopic one. Okay, and now I come to my terminology, because I see mathematics and mathematical thinking in terms of a kind of quadrivium, as in the initial conception. So the distinction between mathematical disciplines has been made for systematical reasons. But behind this classification, the idea is that there are some deeper invariant characteristics which are able to distinguish between different mathematical domains, not by themselves, but in relation to physics. So the two levels that I will talk a lot about is the level of harmonics, okay, where you have this kind of quantum behavior, basically. And this pertains a lot to the domain of time, but not in the ordering, in the linear ordering aspect of time, but what I would call in the frequential and periodic aspect of time. Like, for example, in the case of the harmonics in music, okay, the harmonic frequencies. So the upper level is the domain of harmonics, where time is the basic idea, and the obstacle is usually of a temporal nature, pertaining to the frequential aspect of time. At the lower level, I put the level of geometry, which is, of course, the level of space. It's where architecture takes place. And it is the level where light manifests geometrical objects. So geometrical objects do not exist by themselves in space, but they are manifested in terms of light. And essentially, we can invert the whole thing, so we can think of space in terms of light spectra. The domain of geometry works if we think, for example, about geometrical magnitudes in terms of the notion of a unit. Now, the notion of a unit is not applicable to the domain of time and the domain of harmonics. There, what matters is the notion of a unity. So this is a fundamental difference between a unity and a unit. And it's very important to distinguish about geometrical units and harmonical unities. Now, from a philosophical point of view, why this domain of communication holds the truth of, I would say, the most important theorems of mathematics is the fact that in this domain of harmonics, you do not have the relation between whole and part. This relation pertains to the spectrum, to the light spectrum, so it is a geometric property. At the level of harmonics, what you have are different wholes which are entering together into cycles of symphony. So they synchronize different wholes with different frequencies and different periodicities through time in cycles. But there are no parts here. You have only wholes. At the geometric level, what you have is the whole-part relation. So at the geometric level, you cannot access the whole. What you need is to go from the part to the whole. And this now is a major difference between these two different levels. That's why you need architectonic bridges here that are able to encode this relation between different wholes at the domain of harmonics with the part-whole relation at the domain of geometry. So to prepare you for the next time, I will try to explain what is the idea behind the Pythagorean theorem from the perspective of natural communication between harmonics and geometry.